Hi, everybody. Thank you very much for joining the Zon Virtual Roadshow on milling flexible partials. We're happy to have you all here. We've got quite a program scheduled for you today. My name is Jeff Youngerman. I'm the key account manager for Zon, and we wanted to go through this virtual training. We look forward to someday being able to get back into a real classroom again. I don't think we're too far off, but right now we're doing the virtual training, and as you know, more and more applications are going digital through the laboratory. May not be as smooth digital workflows we would like, but in some cases we even ask ourselves, look, I know we can do it digitally, but does it make sense to do it digitally? Sometimes we perceive it as, well, it's maybe more cost efficient to do it the analog solution. So we know that sometimes what appears to be a great application can quickly become a nightmare in the production workflow of the laboratory. This happens mainly because there are many moving parts of the process and minimal support and training to help get us the reliable and repeatable results. In most cases, when a lab experiences an issue, especially with a new product or application, they hear from the manufacturer, wow, you're the only one having this issue, or, we don't really support that application, or the favorite one is everybody pointing fingers of, it's a software, it's a hardware, it's this, it's that. But in many cases, the manufacturer will even use the laboratory as a beta tester for a new product or a new process. So today we're going to be talking about milling flexible partials. The gentlemen that are going to be on the training are the best of the best when it comes to this part, to their part of the process of milling flexible partials. So, they've all worked together behind the scenes to maximize the software, milling strategies, tooling, hardware, to get the most consistent, repeatable results. So Zon is very excited to be able to work with such partners. I believe that you will not only see the value in the presentation, but you will also identify additional revenue streams for your laboratory. So, at the very end, we're going to be answering questions. Just go ahead and type those in. We would like to save those to the very end. I'm going to turn it over to Chris and let Chris get the program started. So thank you again. And again, if you have any questions at all, type those in and we'll get to those for you. Chris?
Great. Thanks a lot. Yeah, so this is real exciting, guys. I mean, this is going to take you step by step through the process with people from those manufacturers of materials, software, machinery, all the different equipment that's involved in producing one of these. So I think a lot of times when you go to see presentations, you watch webinars, you kind of see, maybe you see a little bit of the whole process, but it usually concentrates on one specific part of that process because, let's be honest, you have a company there and if they have a milling machine or they have tooling or they have a plastic that can be milled, they want to concentrate on that part of it. Well, this is going to have one person from each part of the, each company that's going to take us through that. And I want you guys to understand, these guys work for these companies, but they all have experience sitting exactly where you are. We're going to start out with me, and I'm going to talk about the actual plastics. And it's one company's plastics. You can take all this information and apply it to other plastics that are out there. But specifically, we're going to talk about the Durcetyl, Durflex, and Visit Clear as we go through this. And so I'm going to give my kind of really what I'm going to do is talk a little bit about the material and why it's unique, and then also show you what you could actually create with it. A couple examples of that. And then I'm actually going to talk about how you can actually repair it, right? Because anything that we mill, there's always going to be a reason, especially on the removable side, to need to add teeth later or add a clasp later or repair some sort of a problem. So I'll go over that. Then we're going to move to Carl with 3Shape, right? So all those things I just showed you, he's going to show you at least one example of creating an appliance digitally. And Carl, his grandfather started a lab 100 years ago, and then his dad and his uncle took it over, and Carl worked with them for many years. So he's not only a guy that works for that company, but in early part of his life worked at a lab sitting at a bench. Then we'll move to Mike with CIMSystems, and he's going to show you what Carl created, how you actually position it in pucks, support it, and get it milled. And with Mike, he worked for other companies doing support through design and CAM software. So he did support and training, right? So this is a guy that's trained people how to do this that you're going to hear from, right? We'll then move to Ian. Ian is with Roland Mills, right? So he'll show you how, once it's nested and everything's in place, how nice the mill will work to mill this out accurately and quickly. And then Ian, same thing. His dad has a lab now. We worked with his dad for many years in the lab, right? So this is, again, a guy who knows not just how to kind of, I guess you would say, sell this stuff, but he knows what he's talking about. He knows what we go through sitting at a bench. And then finally, we'll end with Greg. Greg is the tooling, right? So he'll talk about the tooling that works in that Roland mill, size-wise and design-wise of that tooling, as well as the kind of strategies involved to let that mill chew through that plastic nice and quick. And Greg worked at in an earlier part in his life at a very large milling center, right? And his responsibilities were just about everything there, right? So he managed the equipment, the software, the workflows. So he was involved in every part of that. So I think what I really want to get across here is that you guys are going to experience, not a sales pitch today. You're going to experience real information. And of course, you're going to be interested in mills, you're going to be interested in softwares, you're going to be interested in plastics and tooling, I think, through that, right? So it's kind of the perfect combination, the perfect storm of information as far as what I would consider. I would love to watch this thing if I was you guys sitting at home, or in your labs. All right, so enough of a spiel on all of us and blowing up all these guys' heads on how great they are. Let's talk about the workflow and how it relates. I guess basically, why would you decide to mill something rather than do it the traditional way, right? Because a lot of these materials can be processed by injection molding, and we've done that I've done it for 30 years. Why did I, decide as a lab owner to move from, probably, really 100% analog or doing it manually over to probably about 85% digital now. I still have to inject some, but why I made that choice. And the big one is consistency and really time. And I wanted to kind of break down, the analog version of what you have to go through to create something like a Duraflex partial, and the digital side of creating a Duraflex partial, because that's kind of what Carl's going to show you how, or at least part of what he's going to show you how to design. It's going to be what Mike shows you how to nest, and as we go through. All right, so first thing that you need to do in doing an analog version that you don't necessarily have to do on the digital side is duplicate the model, right? You duplicate the model because it pretty much gets destroyed during this process. When it comes to digital, I mean, these things pretty much drop down on the model. There's very little risk of chipping or breaking teeth fitting it. So something you could do, some labs may choose to, may not, but when it comes down to duping, that could be a 2-hour process, right? And I'm not talking about just specifically what you're putting your hands on during that time, but from the time you start to duplicate, you put your model in warm water, pour it up with the hydrocolloid, wait for it to cool, pour stone in, wait for it to set, and then separate. It's a good 2 hours of time that passes there, right? Next, we jump to the setup. Setups could take anywhere from 10 minutes to 45 minutes, depending on if it's a crazy tight bite or whatever might be going on. So if we cut that in half and put it at around 25 minutes on average for a setup, then we jump to investing. Investing is going to take 45. It's going to take 45 minutes to invest the lower, 5 minutes to sprue, maybe 30 minutes to pour up the top and wait for it to set. So you're looking at a total of 1 hour and 20 minutes just to invest the case. Jump the boil out, let's say 10 minutes. Injection, about 30, right? By the time the machine gets warm, you might be able to cut that down to 20 minutes, but 30 is a very safe number. Moving on to cooling, you need about 20 minutes to cool. You can hold it in your hand, it's cool enough. Divesting, you're looking at about 15 minutes. Finishing, again, about 25. I mean, it could finish something as fast as 10 minutes, or it could be a crazy case and the path insertion's wicked. It could take you 40 minutes, right? So you're looking, and we'll cut that in half, say about 25 minutes for finishing. And then polishing about 5 minutes, right? You're looking at, now this is not time specific, like just the amount of time that you're working on that. It's literally the time when you started, the time you're fishing. You're looking at about 5 hours of time that passes. If you jump over to digital, scanning's 5 minutes, designing is around 15, milling is going to be, you know, it depends. If you're milling the base and the teeth, probably all told, you're looking at about 1 hour and 45 minutes. If you're just doing the base and you're going to print the teeth, the base is probably going to be at about 1 hour to 1.5 hours. So that could be flexible. We'll say 1 hour, 45 minutes to give you worst case scenario. Attaching the teeth, luting them together, you know, you're looking at about 10 minutes there. Finishing, like I said, usually just drop on the model. That's the biggie. The consistency of the fit is just amazing, and that's one of the biggest advantages. Fitting, finishing about 10 minutes, and then polishing about 5, right? So you're looking at about 2 hours and 30 minutes, about 2.5 hours. So, you know, if you run into an issue where you got to get a case done, you know, get it out, you know, from start to finish, you could have one done in 2.5 hours, and that's worst case scenario, right? So I think that's the biggest advantage, you know, putting things into workflow that allows for these cases to kind of just not take up a lot of labor. Now, material costs, you're looking at probably, worst case scenario, you're probably looking at about $30 or $40 of material costs. On the digital, you're looking at about 10 or so dollars on the analog side, right? So analog is about 10 bucks. This is going to be about 30 to 40 bucks, right? So there's more material costs, but there's way less labor costs, and there's way more consistency in your end result. I promise you, don't care how experienced your technician is. So yeah, and that's worst case scenario, that 30 to 40. I'll talk to you a little bit about kind of how you can make the most out of that puck that you're using. You know, this is a good example, right? This is our acetyl resin, and we'll talk about materials, but this is a good time to kind of talk about the efficiency and using material, you know, to your biggest advantage. So this case here is, this puck here has a acetyl frame. It's got a bite split, got a 3-unit temporary bridge, and it's got a Nesbit little framework, right? If you add all this up, you know, let's say about 150 for your partial frame, about 120 for your Nesbit frame, your temporary at about $60 a unit. Let's say you're at 180 bucks there, and your bite split about 140. You're looking at about almost $600 in cases milled out of this puck. So, you know, when I talk about material costs, you know, each one of these units shares about a $70 puck charge, right? So now we're down to, you know, 15 bucks or thereabout per case that's in this puck. So when I was saying $30 to $40, that's way worst case scenario. You can really produce a lot of cases out of these pucks. And again, this is acetyl. So the 3 cases that I'm going to talk about today, 3 materials I'm going to talk about today are Duraflex. All right, just so you guys understand, Duraflex is a flexible material, a lot like a Valplast or TCS in its look and feel, but a very different plastic in actually what it is. And we'll talk about that, how it's different in here in just a bit. But it comes in several different pink shades. And VisiClear is the next material. That material is exactly the same as Duraflex in what it is. They are the same plastic. It's just the VisiClear is mostly clear. It has no pink pigment in it. You'll see some examples of cases here in a bit. It's not crystal clear. It's not optically crystal clear. Optically crystal clear actually doesn't do very good in the mouth aesthetically. So, you know, the VisiClear can't be, because it has a crystalline structure in it that doesn't allow it to be crystal clear, but it actually has a bit of a chameleon effect in the mouth. In other words, it's a crystalline structure is what makes it a little bit hazy. When light comes in and bounces back, it gets deflected on those crystals. It actually absorbs the color and actually chameleonizes itself into the mouth. So it's actually a really good thing, but it is something that you have to educate your doctors on when they see it. If they're expecting, you know, VisiClear, they're expecting something optically crystal clear. And lastly, the Zorlux acetal. That is the puck you saw. That's a two-color material, comes in a bleaching shade, B1, A1, A2, A3, A3, 5, and then a C shade. And also it comes in a pink color. The acetal resin is a not very, but it's opaque material. Can't be clear in any way because of the density of the crystalline structure in that material. And it's not quite as flexible as the Duraflex and the VisiClear. So if you need something a little bit, still flexible, but has a little bit more rigidity to it, the acetal resin is a good choice. All of those materials, you heard me mention that word crystalline. All of our materials that we offer from Meyerson, we offer to mill, are crystalline plastics. Those crystalline plastics do a couple of nice things. Other plastics that are out there are mostly amorphous plastics. And amorphous plastics, they allow moisture to absorb. They can gum up when you grind on them because they don't really have a melting point. They just kind of get softer as they get warmer, which means it'll gum up when you burn. The crystalline plastics, Duraflex, Duracell, VisiClear, they actually have a melting point. And so that's why they mill so well. Other plastics, I don't know if anybody out there had tried milling any other plastics, and they'll wind up gumming up your burr if you aren't running water in your mill. And that's because they're probably a nylon of sorts, or mostly amorphous plastics of sorts, and will wind up getting too hot and therefore gumming up, breaking a tool, or making you stop your job. To kind of explain what I mean by crystalline and amorphous, this has always been a really good slide. Crystalline plastics are very dense. All the particles are densely packed together, so there's no way for moisture to actually permeate the material, so it stays stain-free as far as internally, and doesn't absorb moisture comes with that bacteria, stains, and smells, right? It's why it can be 100% dense, but still be flexible. Amorphous plastics, like some that are out there, the particles have a lot of gaps in space. Actually, why it can be flexible. Something like Valplast or TCS, when you flex it, it's actually squishing those bubbles, and that's what's allowing for that flex and movement. The problem is those gaps in spaces allow moisture and stains of bacteria. And if you guys have worked with those plastics and you see them come back for repair, you'll notice real quick what I'm talking about. With the Duraflex, Duracetal, and VisiClear, but Duraflex specifically on this slide, that we did some testing, and over a 24-hour period, the Duraflex, it's 0.05. That's as close as nothing as you can get as far as absorption. Other flexible material that we tested alongside of it had absorbed 1.30% moisture at that time, and that was at, I believe, a 24-hour period, and it was still going. It was actually still rising at that point, so it probably would have absorbed. And so again, it's important to make sure something that's going to be in the mouth long term isn't going to pick up stains and deal with that. One way to kind of know that, our materials will float and they'll stay floating. Other materials you put in a car may initially float if it's been dried out, but eventually it'll sit there and then it'll absorb moisture and drop to the bottom. So that's one good way of testing what material you're working with, is to see if it's closed. We did some testing with the Duraflex, putting it in different materials, liquids that would stain. Can't see it a little, you can see it darkened up a little bit. It's not a great side, but of course, the problem with absorption of moisture is if you drink a lot of wine, coffee, tea, whatever it might be that's dark, it's going to absorb that, and with it's going to take that pigment and can discolor the appliance. That won't happen with Duraflex, VisiClear, or Duracetal. So now what I'm going to do, now you have a little baseline of what this material is and why it might be an advantage to use. I'll kind of give you some examples of different appliances that you could make with it. Here's a VisiClear framework. Now this is not, this is kind of a little different from what you're going to see with Carl, in that he's going to make a partial sockets so that you have a tooth actually luted down in place with a socket. This is another alternative way of processing a flexible partial, where you have a meshwork with an external and internal finish line, and like a metal frame, and then you process acrylic saddles to those areas. Both of them have their advantages. This should be a more expensive lab fee to your doctor, because you have to make a frame, you then have to set the teeth, you then have to process the acrylic, right? With what you'll see with Carl with the partial sockets, you kind of just have to mill the base and then mill or print the teeth and lute them together. So it's less labor, right? This should be your premium, and the socket should be your competitor of what you would do last type. So this should be an advantage to this is, let's say there was some extractions being done or something like that. Doctor has that acrylic sitting there that allows you to do a reline, even chair side to that other side. Let's say a patient gets some sore spots, could do a soft reline. So that's the nice thing about doing these frames. And then you also get some doctors who just hate the idea of that flexible partial. They've had a bad experience, and they're like, I like metal. But the problem with metal is aesthetically and comfort and stuff like that. This is a good alternative for them, especially acetyl resin, which you'll see in a bit. The acetyl is a little bit more rigid. So it's like, hey, this isn't as rigid. We have tooth color clasp. We could keep them off the tissue if that's the doctor's issue. The rigidity allows for a more closely stabilized version of this compared to metal. So it's really just having that option to offer to your doctors. The Duraflex, as well as what we talked about, the VisiClear, actually has that chameleon effect. So it does have the pigment, but it will blend in nice. This is it's going to receive a Duraflex partial. It's interesting. This case, this was I went to a course in England, actually doing a table clinic there, and this guy brought that case and said, hey, can we do this? He was from Denmark. And I was like, well, no, we're not really doing a full-on processing of a case here, but I'll take the case back with me and I'll work on it. And I knew he had done a really good book on contouring, customizing denture bases. And so I said, hey, give me a copy of your book. I'll do the case for you. We did that, and he loved it. And so he sent me a picture of this, which was his first case. So there's the case not before, and here it is after. And I really like this, how the saddle, again, chameleonizes itself, blends itself in, kind of picks up the color of what it's sitting on. Here, he made this clasp kind of come up a little high, could have faded that off. But even that clasp is picking up the tooth color, right? So it kind of has a little bit of a, I don't know what you say, fudge factor for slight little differences or mistakes. So that was a really good example of how the Duraflex blends in. This was a good example of the clasps to show kind of what we talked about there, where here, where it's thicker, it has more of a pigment pink showing. Here on the tooth, it's a lot like how a canine and a tissue would be. It kind of blanches a little bit there and really shows a nice aesthetics as it goes around the tooth. This case here, a little unilateral, is I really like this because it shows, again, a little darker, redder tissue picked up that color and blended itself in. So a couple examples of how this material really blends itself in to its surrounding, that chameleon effect. Here's our acetyl resin, again, framework design. I wanted to show you this and how clean this material comes out of the mill. When I talk about not needing much finishing, also you don't need much polishing. The material comes out almost shiny, right? So you have some little stragglers, little hairs and stuff, but you're going to be cutting that off and smoothing it. It just comes out of the mill really nice. Here's an example of kind of a combination of a partial, and if you guys have heard of Snap-on Smile, it's kind of a combo case, right? We have a partial and saddle meshwork on the posterior, and then in the anterior, we're sliding over these teeth, right? And here's our end result, right? So because these materials come in tooth colors and multiple tooth colors, it gives you a little bit more options, allows you to expand your mind a little bit as to what you could actually create. And digitally, this is really relatively easy to create through 3Shape. Again, we started talking about Snap-on Smile. Contact your Zahn rep if you want more information on becoming certified to process the Snap-on Smiles, but it is made out of acetyl resin. And it's a really nice tool. I mean, Snap-on Smile aesthetically, you have to have a mouth that's, you know, if you have a smile range of 1 to 10, you know, 1 being very ugly, just the ugliest smile, and 10 being the most beautiful. If the patient is a 1, 2, 3, you'll probably get them up to a 5 or 6 within a Snap-on Smile aesthetically, right? And they'll be very happy with that, right? That'll be a huge change. If the patient is a 4 or 5 and you get them up to a 6, they're not going to be happy, right? But it's a really good tool for opening bites. And that's kind of what you see here. This patient had a collapsed bite. Doctor created a bite, reestablished their vertical, right? Here's their collapsed bite, and here's where we put them with the Snap-on. And so it's just a really nice tool to use that way as well. And that's, again, can be designed and milled easily. Unilateral, right? I mean, I don't know, unless the patient has really bad dexterity and you're worried about them swallowing or inhaling a small appliance like that. But a unilateral, I don't know why anyone would do a flipper again. You know, these can be milled, and the cool thing about these, it's all one piece, right? The tooth, the clasps, everything is all acetal because it comes in the different shades, right? And the cool thing about these unilaterals is they don't take up much space, right? So moving back to the puck that I showed you at the very start, there was actually a little space left on that puck, and that puck would have actually been able to fit. You know, we talked about 500 and almost $600 was milled out of that puck. There's room. I could have probably stuck this unilateral, the other one, over in the side. Now we bumped it up to another, you know, $700 or $750 worth of billing. So really, you can be really efficient. You know, the Roland with CIMSystems really does a good job of logging your pucks. So all those used pucks you can keep in your library, and whenever you get a, you know, an A1 little unilateral, you can look through your inventory in the software, find that puck that has enough space, stick it in there and mill it. And you can really use up that material and make for really, you know, we're all in business, right? So we want to buy these pucks, right, from the distributors, you know, from Zon, and they want to sell them to us. But as technicians, we want to use the heck out of them. We want every, you know, millimeter of space used on creating appliances, so we make our money back. So that's kind of just a nice overview, maybe to get your minds flexing a little bit on what you could actually accomplish as far as creating things with these different plastics. One last thing I want to kind of end on is there's the hot shotgun. This is a little handheld injector, so you guys may have it out there. It will work on these millable plastics the same as it does on an injected one. So what I mean by that is the plastics are slightly different, but basically the same. So in the future, if the patient loses a tooth, needs a clasp added, something like that, you can actually add a clasp on, add a tooth using the hot shotgun. Right? So let's say you lost a clasp, whatever reason, right? We need to add a clasp on here. Let's say the doctor wanted a clear clasp on a pink frame. For whatever reason, they want a clear clasp on the front of VisiClear. VisiClear and Duraflex are the same thing, right? So they will bond to each other, and they'll melt to each other. So you wax your clasp, use this little torch. This is from Blazer. It's called the Excalibur model SI100, just blows out hot air. And you'll add, if you need to see a video on this on Myerson's YouTube channel, there's a really good video kind of showing this live action. And here's your clasp added on. Here it is cleaned up, and there's 100% bond between the clasp and the base. So you can add teeth this way. You can do a lot of different repairs. All right, so that's everything for me. So what I'm going to do now is switch over to Carl. So hopefully that gave you some insight into, when Carl showed you kind of some of these designs and some of the things you're going to see there, hopefully that gives you some insight into other things that you can create, because of course Carl's going to show you, one example. Hopefully that gave you some other examples of things that you could design. And like I said, it's amazing how your mind really starts to to branch out once you know what you can actually create with that. So, all right, I see Carl's show is set up. We'll now listen to Carl and see some cool stuff on 3Shape.
All right, thanks, Chris, and thanks everyone for coming. Super excited to show the 3Shape part of the RPD process for a flexible frame. My name is Carl Horrocks. I'm the business development manager for Lab for 3Shape, and we're going to walk you through the removable overview of what 3Shape has to offer. In particular, we'll discuss the RPD workflow. But then we have some exciting things to show of what's coming soon. Actually coming out this month of June is the next version of 3Shape, our Dental Systems 2021 software. And being that, removables in general are a hot design topic, we've spent a lot of resources updating the RPD and denture workflows. So we have some good updates to provide to you. So look out for the next version, and you should see some social media posts of some of the latest features. But here we are going to show you today. And then we're going to wrap up with a little demo of RPD, kind of everything Chris discussed earlier. Took a couple screen videos of the process to save time, because I know we have the rest of our presenters lined up. So yeah, I think we got a good little spread for you guys on the 3Shape workflow. So first, and again, everything what Chris said earlier about comparing analog to digital is very similar with the 3Shape process. So basically taking a look at global production of removables, and this is dentures and RPDs. Digital adoption is quite low, but now with all these new materials and manufacturing processes and scan and design, this should be something you guys are looking at or learning about to adopt into your lab. But for the most part, why digital? We all know, what digital has to offer, better accuracies, better results, on the clinical level, chair time, but on the lab level, it's time. And pretty much in line with what Chris explained, digital takes about 2.5 hours. Conventional, I think he mentioned around 5 or 6, but we're right in that ballpark. So a big time savings, and one of the things in today's day and age is you can't get time back. So saving time is huge to do other operations in the lab or move on to other cases. And the big advantage with digital is replicating, keeping records of everything, having it files saved. You can reproduce very easily. If the patient loses it or if it breaks, just it's already printed or designed, either print or mill a new one. So moving along to where 3Shape is with removable designs, right? So we just talked about, the 50 million removable cases done globally, about 2 or 3% of them are digitally, but a huge portion of that is done in 3Shape designs. And year over year, we've had a huge growth from our users in these types of designs. So when we speak removable, we think of full dentures, partial frames, but also custom trays are a removable option as a 3Shape indication. And this is what was designed in 2020 compared to 2019. And we all know we lost a few months in 2020, but we've still seen a huge spike in these types of design cases. So other laboratories are getting out there and doing these types of cases digitally. So really happy to share our workflow and you all participating in this webinar to learn more about it. But it's pretty impressive what the global removable community has been doing digitally over the last few years, and a big increase in adoption. So with that, now the next step is to getting into it and doing it. And what are the steps and workflows to do a digital removable? Well, it all starts with a scan. Whether you're using a lab scanner, which 3Shape has 4 different lab scanners in our portfolio. Our E-scanners, they range from an E1, an E2, an E3, and then the most accurate E4. And some of these scanners actually pick up texture, where you can draw on your model, and the scanner will actually pick those drawings up. So, transitioning into a removable workflow is very easy when you trace your model with the outline of a clasp or a connector, and then the scanner picks that up. It's very easy to design from that. Or if you're working with clinicians who have adopted digital, scanning with an intraoral scanner is now possible. And 3Shape offers a 3Shape Trios intraoral scanner, which is best in class for acquiring for partial cases. Trios has been a great scanner for those wide span edentulous spaces as well. So step number one is acquire the data, either directly to the patient with an iOS or with one of our lab scanners. Next, in the workflow, the case has been digitized and now walks us through our software, where 3Shape has a really nice user interface, really nice tools and workflow that guides the designer from step one of insertion direction, to outlining the restoration, the framework, choosing the teeth, setting up, and then some sculpting tools to put your finishing touches on it. And then last but not least is the manufacturing side. We're an open sourced file format. So 3Shape produces an STL file that can then be placed in the CAM software, which Mike will walk you through later, and then into a Roland mill, and which Ian will walk you through as well. So a really nice workflow, and you'll see a little bit more on the step 3 on the manufacturing side later in this presentation. So taking a look at step 1 in a little bit more detail, right? So we talked about lab scanners, acquiring analogs, models or impressions, and then with iOS scanners with Trios. So our lab scanners can take a variety of different models or impressions to scan, whether you're setting up perhaps a denture case with a wax rim. We can acquire that data as well with scanning both upper and lower models and then your wax rim for the occlusion. Or if you're using an impression, we can scan impressions directly, and then the software will convert that impression scan into a 3D printable model, where you can go ahead and make your restoration and then mill your frame or denture, and then 3D print your model, and then everything fits together really nicely and accurately. And then on the iOS side, the direct intraoral scanner, Trios has been very good with scanning edentulous, but with RPDs, patient has teeth to begin with, so it's even easier to scan direct in the patient's mouth. So, that's the quick overview of acquiring the data. And now let's dive into step number 2, where it's the software side of things. And the next couple of slides, we're going to go through what's new in the latest version of 3Shape. So this is a little sneak peek to what's coming and what we've added to the software. So again, look out for the latest update. It should be getting pushed out later this month, and then check with your reseller to make sure that they'll provide you with the latest installer to upgrade. But for the most part, a lot of great updates within the removable modules. And number one, probably one of the biggest requests out there from the last year or so is the flexibility to design a full denture and a partial all in one case. So now in the Dental Systems 2021, we can handle that. Used to have to be broken out into 2 orders, but now we can do a full denture and a partial all in one order and one workflow. So again, more efficient, just more convenient for our users. What also we've improved on is the tool selection and the workflows to be similar between full denture designs and RPD designs. So now we're utilizing the same tools across both modules. So the same smile composer to set teeth up, utilizing the same tools that are in the smile composer between full dentures and RPDs. Placing gingiva in the design, very similar between both modules, and the tools are very similar as well. The ability to bridge teeth. So either designing single teeth that can be luted on, like Chris spoke about earlier, or you can actually bridge teeth, and then they're in a little bridge, and you can mill those as well. And we're also have the ability to use denture tooth libraries from some of our denture tooth partners as well in the full denture module and the RPD module. So taking a look at some other updates with the removable modules and RPD as well. Just some more customization tools. The ability to add texture to the gingiva. In the past, a user would have to sculpt it by hand, but now we have a stippling feature to stipple the denture or RPD. The user paints on an area on the CAD file, and then chooses the stippled pattern, and then the software will place that pattern on where the designer placed that that highlighted area.
Hey, Carl.
Yep, go ahead.
Yeah, it's Chris. Hey, one thing I wanted to bring up that was kind of key is the fact that you can bridge those teeth together. That's really nice, especially when it comes to flexible partials, because when you lute those teeth into their sockets, you're relying very much strictly on a mechanical retention. So having those teeth splinted together or bridged together allows them all to kind of use each other for retentive strength to stay in place. So that's really nice. I like to hear that.
Yeah, great. Thanks. Yeah, thanks for pointing that out. Yeah, so again, another feature that's coming just shortly. Let's see what's next. So we talked about the texture and the stippling. Oh, the custom ID now. And some states require this on their dentures or RPDs, and now we have the ability to add in the software an ID. You can either place it as a negative or a positive, just depending on how if you want to burr that off or smooth that out after the fact, just so you know where or what restoration is when it's in your puck or printer. But yeah, just another option added to the tools in the next version of software. And one of the other updates that we've provided was the ability to add a smile design or a mock-up that maybe a clinician did or you assisted with prior to the patient accepting the treatment. And 3Shape has a 2D smile design software. So now you can overlay that mock-up or that smile design with an RPD case or a denture case, just to help with some anterior setup and seeing what the patient and the doctor discussed and agreed upon. You, the designer, can now use these pictures to help set up cases digitally as well. All right, so I hope everyone learned of the RPD workflow of scan, design within 3Shape. Hopefully some of these new features will help you either with your current digital RPD workflow or now you've seen what's coming. You're like, okay, now this is great. I think I'm ready to make the jump into transitioning into digital. So hopefully we can make that happen for you guys. So next we have a little RPD demonstration just on to save time. Like I said earlier, I took some screenshots and some videos of the RPD process after it's been scanned. The design process pretty much takes 7 steps in the workflow, and we'll go through those one by one. And the first couple steps are very easy. It'll take a few minutes to do these steps. And the first step, number 1, is setting your path of insertion. I'll pause it right there just to talk a little bit about what you're seeing on screen. So you, the user, will rotate the model around so you're looking at this path of insertion, the view itself, and then down to the bottom as well, you have some other view or vantage points as well. Now, when choosing your path of insertion, you'll rotate your model and look down on top of it. You'll see these arrows. You'll also see down the bottom as well, you can set up different views. And you have some tools on the left, either set from view, where you can set it yourself, or you can use the arrow keys on the left-hand side to move the path of insertion in increments of, single degrees, or what I have set up here as a 5-degree increment. So very easy digitally to, set your path of insertion. You see the undercut depths as well, change on the fly when your different paths of insertion changes. So with 3Shape, just going to stay on this page real quick. If you notice up in the top, the workflow bars, so we've jumped right into our path of insertion and block out, but some of the previous steps we could have done some extra model handling, where if we have an immediate, we have some virtual extraction tools that you can do digitally as well. And I'll mention this in the future in the next couple of slides, but with immediate cases and virtual extractions, the best thing with digital is we have an undo button. So if you make a mistake, you can always undo it. Where in an analog world, if you make a mistake, it's going to set you back some time. But yeah, so just bringing back, fast forward to the survey and block out. We set our path of insertion. Now we hit next, and the software will then automatically put some wax and block out. And now we have some sculpting tools, or a wax knife, where we can remove wax, we can add wax. Let's hold this up right there for a quick second. The nice thing about digital with the wax knife is we can be very precise. If you look on the left-hand side where I have the add wax on, just below it, I have a threshold of 0.4 millimeters. That means I'm only going to add 0.4 when I paint this wax on. So you have that control with digital, and evenness across, all the application. So again, just showing you how you can add some wax on. You can smooth the wax, you can remove it. You obviously see all your undercut depths, and you're just going to remove the wax, from where you want your clasps or your restoration to sit on as well. So very easy to do that, and you have a lot of precise tools to be able to add or remove the exact amount that you want. So after we've done that, our model, our case is set up now to design the teeth. So when we hit next, if you're looking up at the top workflow bar, we're now in the tooth selection up in the middle. So we're almost halfway through our design. And with this is a smile composer. With 3Shape, the smile composer is the main step in the workflow, no matter what type of restoration you're doing. And we know that users might have used a crown and bridge module in the past, and now they're getting into removables. So we wanted to make the tools very similar to what our users have known in the past. So this is the same exact smile composer. If you design crowns, that now you're designing a partial with some teeth. So trying to keep everything very similar across all the designs. So we're gonna hit play, and I'm just gonna walk you through some of these tools. The first is our smile library, where we have a vast amount of different of teeth sizes and shapes to choose from. We have filters where you can choose between the different shaped teeth as well. So very easy to pick and choose a library that fits this case. Once you do that, we have some tools that we can size and rotate and move, either using the little handle pinpoints to move, or I'm just going to jump back one more step here. just to show you when we're moving some teeth. So these little handle points, when you click on one of the handles, it'll actually show you a degree table as well. So you can really fine tune your tooth movement and placement as well. Next, once you got the teeth in place, we have a wax knife. Again, very similar to what we did with the wax knife with the block out. You have the same tools in the wax knife. If you look on the left-hand side, add, remove, smooth, and the thresholds. And here I'm just showing how easy it is to smooth out some anatomy. And like I said before, your biggest friend in the digital world is the undo button, because everyone makes mistakes and we learn from that. But in the digital world, we have the ability to undo it. So here I'll show you, smoothing out some anatomy, going on to the left-hand side and undoing that, and it brings it right back in. Now, for some more gross movements, maybe cusp tip placement or marginal ridge placement, we have a morphing tool, which will allow you to, grab that tooth and stretch it into place. Now, what's nice within the 3Shape workflow is we're going to design the teeth first. So you get a good understanding of where the teeth are going to sit on the case. And then we're going to go into designing of the frame. And here we come into the frame design. Now, you see on the left-hand side, we have a couple workflow steps, right? So in the case setup, we chose a RPD with teeth. Within 3Shape, we give you all the RPD designs if you were going to design a traditional metal frame with a retention grid and clasps and finishing line. But for this flexible, we don't need to do that. So we could skip right over that first retention grid step on the left and go right into a major connector. And with the major connector, we're just going to draw on the model. Now, if you used a scanner that can pick up texture, we could have drawn on the model, and all we have to do is just follow that line drawing, to draw our frame here. But we have some tools where you can move the dots individually. We have tools where we can use a editing tool, a fast editing tool, and draw it in. We can switch back to the individual dots. So you, the user, have all these different tools to do gross movements, to do micro movements, right at your fingertips. We also have some thickness settings as well, so you can be very accurate with your wax thickness in the digital space. All right, so we're getting close now. When we hit next, the software will then build out what we just drew in. Okay, so with all those lines where we drew, the thickness that we told the software to make it now builds out our frame here. And then, like always, 3Shape, we always add a sculpt toolkit. Again, very similar to the previous wax sculpting that we've done in the past. A few steps where with the adding and the removing and the smoothing, and it's a very nice ease with your mouse to brush on any adding or smoothing or removing of thickness of the wax. Nice thing too is we have control of the amount of material that you can put on and the area. So with this, just jump back a step here. Oops. Let's so if I put my cursor right here and we'll stop it. If you see where my mouse is on screen, I have a little red circle. Well, the software is only going to add wax just inside that. And then if we jump ahead a little bit, when we chose the smooth, you can make that circle bigger, and then you're smoothing out a larger area for a little bit more speed and efficiency in the design. So again, just some nuances about each little tool, and you guys have the flexibility at your fingertips. Now, with the designing, you have the option to add some mechanical retention with these glued-in teeth, kind of like what Chris was talking about previously, or if you were to bridge this case, having these two units combined adds a little bit more retention as well. But we can build up at the inside underneath the teeth, and everything will get adapted to one another. But this step of the design is just, again, like always, we always add a sculpt toolkit, and in the sculpt toolkit, we have wax knives. This is a stippling feature where we can paint on the area that we want stippling to be. We can choose our pattern. We hit the play button, and within a few seconds, we now have stippling on our restoration. And our good friend, our undo button, we can remove that easily. And just showing you some features with the new ID tag, you can add that as a positive or a negative onto your case. And here's the last little tool. This is where the contacts and smoothing get brought in, where we can add some little retention spots for these glued in teeth, where on the intaglio of the tooth as well, we'll have a cut in that will fit perfectly into that little socket that we made on the frame here. And then that's basically it. I mean, that's the steps to making a frame. The last thing is it brings you into where we're going to save our case, and the software is going to produce STL files of the frame and of the teeth individually, because we kept them as individual teeth. But if we were to bridge them, they would be one STL file. So it gives us one last overview of our design, where we can, lift off the teeth, just double check everything. And if we have met the minimum thickness requirement by the material, we get these little green checks on the left-hand side. So on the left-hand side, we got a little green check of the frame and a green check of the tooth. So that means we've designed everything to what the material company and our mill will allow for. If I designed anything too thin, we'd get a little warning or a message that would say, hey, the material you're using, the mill that's going to manufacture this, it's not sufficient. And that'll trigger us to, go back and take a look and add material if necessary. But for the most part, that is the the 3Shape workflow of the RPD. Hope we learned a little bit of the 3Shape, and hope you have a better understanding of what we can do and the features that we have to offer.
Great, thanks, Carl. Yeah, I think you've worked with several different design softwares, and there's no doubt that 3Shape covers all their bases. What it has to offer for you to be able to create, to just the finished product and the speed of being able to design. So, and I think we saw a really good example of that there. Without you talking, that probably would have taken you 5 or 10 minutes to design that guy up and get it ready to move over to your mill. So yeah, thanks a lot. And now, so now we're gonna have Mike come in, Mike Webb, and he's gonna take that project over and show you how to nest it and talk about that the CAM software. Go ahead, Mike.
Great, thank you, Chris, and thank you, Carl, for walking us through that process and kind of outlining the workflow. So as Carl had mentioned in his presentation, we're now at step 3 of that process, which is essentially the manufacturing. And today I'm going to show you a Millbox dental CAM solution where we will nest these parts, essentially preparing them to go on the machine. It's often an overlooked but very important step of the process, as it's going to affect everything that occurs down the line in terms of post-processing, the success that you're going to get of this part coming off the mill, and it being able to simply snap onto your models and work. So getting right into it, I'm going to go through a couple different slides here to kind of explain the structure, and then we're going to kind of do a demo to show you how that would be processed. So one of the most important things when it comes to Millbox is staying current on your annual updates and annual maintenance. It could be not necessarily just Millbox, any CAM in general. You want to maintain updates. And here's just kind of a brief preview of some of the main features that we've released year over year in the CAM. So think of your CAM software just as you think of the CAD, as it's a constant evolution. There's a constant improvement occurring behind the scenes, even not necessarily that you as the end user will have to make those improvements, although you can. All the settings for how we run the machine, those are actually customizable, mostly by the dealers. And in this particular case, with Zahn, for example, they have their own custom installer that has all of the custom parameters built in. And in particular, specifically for some of the materials we've talked about today, like VisiClear, acetal. And so in the older versions, before those materials existed, you may not necessarily have those as an option. And that's very important to mention because you can't really necessarily use a standard PMMA strategy with these materials because they hold on to those thermal properties a little bit more. The material will start to gum up during the machining process. So it's very important that you're running the right settings for your material. And if you do run into issues, like let's say that you're not necessarily with VisiClear or acetal, but let's say you're stepping out to some other similar type material, or whatever your preference is, it's important to watch whenever you're loading new materials in the machine. You want to watch, listen to, and understand if it's cutting in the manner that it should be. And some telltale cases, and I think that maybe Greg can touch on this when he talks a little bit more about the tooling, is you'll see that material residue either sticking to the part during the machining process, or it might even be sticking and gumming up on your tools. And that can really spell some bad results for us. So all kinds of issues ranging from parts that don't fit to broken tools and things like that. So it's very important that we're following the proper process and using the proper profiles. Maintaining your software up to date will always ensure that you have access to those new profiles that come out as they hit the market. And then talking about what actually occurs now on the nesting side. So here we see a screenshot of Millbox. Essentially what we're going to be doing is importing this file into the CAM, putting it in the block, telling the machine what features we need to be milled out. But before we import it, this is a very important step also. Before we import our parts, we want to check to validate that their orientation is correct, because there's a predefined milling strategy that's programmed in the CAM software, which means that we're coming in from the top and we're coming in from the bottom. And there's certain features that we're looking for on the top. Let's say like the occlusal, the occlusal sulcus. We're typically looking for that the anatomy on the occlusal side. So those tool paths won't exist for the 180 side. So imagine if it was, we could be talking about a denture or a bridge, something with anatomy. If that part is flipped upside down, your 0.6 tool, your 0.3 millimeter tools are going to come in and try to mill it from the top side of the machine. In this case, that would be the prep side of your part. So in that case, you wouldn't get the desired result. In fact, the part may look like it's slightly unmachined throughout the milling process. And so this is why it's important to check your orientation, because the operations don't necessarily know what the occlusal of the part is versus the prep side. And then when you're looking at your part in the preview, so when you select your STL file here, we give you a little preview in the bottom right-hand corner, and you can see the part and how it's actually oriented. You should see your occlusal surfaces oriented toward the top in the Z-axis. So if it appears on screen as is, that's good. You know that everything is fine. Sometimes certain parts may come in on their sides or oriented a little bit differently. And here you can see from the preview that this particular denture tooth is imported on its side. And that has to do with how it was output from the CAD software. We constantly work with either 3Shape or ExoCAD or whatever mainstream CAD systems that are out there to ensure that they're outputting the files in a way that's conducive for milling. So we often will give them feedback and stuff like that, but also this could be just a matter of changing the settings. I know in ExoCAD, for example, there's a default settings.xml file that allows you to ensure that all of your parts are always output with the occlusal facing positive in the Z-axis or facing up orientation. On the 3Shape side, there's a couple different options for additional output files that you can do, like PTS files, and we'll get into that at another time. But I think right now it's just a matter of you'll have to double check your STL file as it's being imported, and then if you need to make changes to that, we actually have built-in utilities to Millbox. In this case, Lab 3D Explorer. We can then rotate that file. And again, I'll show this to you guys in real time so we can kind of get a good grasp of how that actually looks. And then, of course, nesting your RPDs. Some of the main things that you're going to want to take into account. It's not rocket science, but there are a couple different items that we'll cover, and we'll talk about specifically why I chose to use the support pins that I used in this case and where I decided to place those and my rationale behind that. As far as nesting the RPD or denture teeth, there are again some pointers there as well. The main item that we're going to be keeping in mind here is that we want to, sometimes you can tell just by looking at the STL file where that socket will interface with the tooth. And that's essentially what you're looking for. You're looking for those steep angled walls and you want to avoid placement of your support pin in those areas. So that way you're not having to adjust these teeth to get them to fit into the denture base. Of course, this is not a problem if you're talking about maybe 3D printing these teeth that are going to interface with the RPD, because then you don't have to worry about a support pin that has to be removed after the fact. So let's go into the software here and continue along. So here we have Millbox, and essentially I'm at the very first step of the process. I'm just going to choose my material. Now at this particular phase, I could choose to use acetal or VisiClear, and as I scroll down, I can see that the material visualizations change appropriately based off of what I'm working with. So in this particular case, I can import, I can choose between a C-clamp, open face C-clamp. This is really good if you want to mill away the collar of the disc, and we can come in and get a lot of facial anatomy. For RPDs, not necessarily a huge benefit, but it can help out if you have teeth, for example, like that snap-on smile that Chris showed us earlier, where you're going to have emergence, you're going to have the emergence, the gingival tissue, all of that. So in order for that to be milled out in the best way possible, we typically can mill away the collar of the disc. So here's an example of a denture base where we milled away the collar of the disc, but you can see it gives us unparalleled access to the facial aspect of that restoration. And that can be key to preventing a lot of extra handwork after the part comes off of the machine. So once we've pulled up our machine, we've selected our material. The next stage we're going to be brought to is importing our STL file for milling. So this is the file that Carl would have produced from your 3Shape CAD system or whatever CAD system you're using. This is just the file explorer, so I can navigate to where that file is located. Here we see the preview, as I showed you earlier in the presentation. And if I click on that preview, we actually get a 3D preview or viewer window that we can then open up and do full rotation on the part. So you can see there's that stippling feature from 3Shape. And then we can kind of get a good overall look at the part. But what you notice is when I clicked on the preview and I just kind of rotated it just a little bit to see where my occlusal was, it was automatically aligned with where it needed to be. So this part is actually right side up and there's no issues here. Yeah,
Mike, I think one thing that's nice about that window too is it shows you the Z height. So you know right away what size puck you're going to need to be using. I really like that.
Precisely, yes, and thank you for mentioning that. There's a couple different things that we have available here. Is not just the Z height itself, but we can actually, because our machine is a 5-axis machine, you know, if we can optimize by 15 or let's say 20 degrees, whatever the machine's limits are, we can actually reduce the height of this part taken up within the disc. So normally I'd have to use, let's say, a 12-millimeter disc, but when I use that 5th axis on the machine, you can see that actually reduces down the height taken up, and now I can fit this confidently into a 10-millimeter disc. And so not only am I saving time by machining it out of a thinner disc, which means less material to rough away before I can start my finishing, but I'm saving space in the disc, and I'm not spending all that extra time cutting unnecessary material. So thank you for bringing that up. As far as the denture teeth, I'll pull those up in a separate job, but you can see as soon as I click on these, they're already on their side. So the orientation is not necessarily ideal. So we'll come back to those and we'll get those teeth, but for now I'm going to import this RPD framework and we're going to walk through how I'm going to place my support pins or what the strategy is for placing these. It shouldn't take long because it's a relatively small part. but there are some key points that we want to pay attention to. And so what's going on right now is we're importing the part. Millbox is kind of detecting if it can be adjusted in the Z-axis or rotated slightly to make it take up less space within the disk. Chris had mentioned earlier, if you have partially used stock, here's a good example of that, where I've milled out of a test blank previously. And in particular, this RPD, I'm just going to mill it in here again, but we see a representation of what's actually already been cut out from that material. Millbox actually takes this a step further. So if I had 10 or 15 disks available, it would not only look at the disk that has the most space available, it actually looks at the disk that has the right amount of space available. So if, for example, my disk is 99% used, it will actually skip that disk and go down to the next disk in the list to see if that RPD could fit in here. And it will actually automatically suggest that material for me as the end user. So I don't have to go hunting through and taking my best educated guess. The CAM kind of takes that responsibility off your hands. And that's one of our, talking about some of the later updates, a lot of what we focused on, which I know 3Shape is focused on heavily this year as well, is artificial intelligence and AI. And literally taking those manual steps that you would have to do in other nesting software and doing those for you, or alleviating those steps, so that way as an end user, it's just one less thing you have to worry about. But it is equally as important. So we can see that here's my RPD, and this is the one that Carl designed. And in this particular case, it's just kind of thrown in some basic supports here. And when it comes to RPDs, there's not a really good auto nesting solution for that today. So in this particular case, I'm going to go in and remove my support pins. So by selecting my part, I kind of get these options. I can like come in and add support pins if I want. What I'm going to do is I'm going to hit this little delete support pins, and it allows me to delete all the support pins of this selected item. So I'm going to say yes, and that gets rid of them. Kind of gives me a clean slate, so I can kind of get in there and do what I need to. I'm going to turn the fixture off for the machine, so that way it's kind of out of my view as well. And now I'm going to go ahead and start adding my support structure for this part. So the main thing that you want to keep in mind is when it comes to milling flexible partials, especially in materials like VisiClear and acetyl, these materials are a lot softer and a lot more flexible. So throughout the milling process, you really need to think about the rigidity of how you're holding on to these parts and whether or not there's any potential for flex. So I like, and this is personal opinion, and this is, so you don't have to do this, but this is what I would recommend, just my personal style, is I like using the smart support pins. This is a more recent implementation in Millbox, but I think at least 2019, 2020 customers have access to this, where we'll actually, so what you're seeing here, first of all, is when I'm placing my support pins, we see this little white line get projected all the way around the part. And for technicians, you can, in some ways, you can kind of consider that almost like the height of contour. We call it the equator line because it really depends on how the part is oriented in the disc. It's not really about the height of contour per se, but more or less where the 0 side toolpath ends, the top, and the 180 side picks up. And that's important information to understand because where we decide to place our support pins, we could potentially be placing undercuts. And this is also something that Millbox does really well, is it helps you kind of visualize that. So these blue shaded areas on my RPD are telling me, hey, those are undercut areas. The spindle can't see that from the 0 side or from the 180 side. So the only way those can be milled out is if we're doing 5-axis external undercuts for machining the outside of the part. And the same is the case for support pins and my placement of my support pins. So if I was to put one here, for example, the reality is if I don't mill the undercuts on this machine, I'm going to be left with a large ledge of material leading from where that undercut begins straight all the way down to the support pin. And that's going to be a lot of excess material for you to have to finish off after the machine has completed its cutting. And so we're trying to save time. So again, just utilize these tools in this visualization to make sure that you're placing your supports where they need to be. And another reason I like these smart support pins is because they morph according to that equator line. So if you've got, again, this is all in the effort of minimizing undercuts on this particular part, but also reducing the amount of finishing that you have to do. Because if you're talking about a round support pin, look at how much more material above and below that equator line actually gets removed, versus this one, it's only 0.5 millimeter along the equator line. So you're, again, minimizing your post-processing steps there. And you can use a mixture, so you don't have to do all of one or all of the other. In particular, we mentioned about flexibility being an issue here. So, you know, ideally, like if this were, not zirconia, but if this were like standard PMMA, then usually that would be rigid enough. I'd feel confident that my supports here are good enough. The other thing I like about these types of supports is that it provides more support, I guess laterally, you would say. So it prevents this type of rotational flexing that can happen with a round support pin, if you can imagine. So the other point that I would do on this particular case, just to finalize my nesting here, is I would come in and add a round support pin, and I'm going to make this one cuttable. So I'm going to make the diameter at my material slightly larger, and then I'm going to make it taper down to, I say a 2 millimeter should be more than sufficient. And then I'm just going to place it here on the part. So, and essentially, again, this is to prevent the flexing that could occur here in the center of this RPD throughout the machining process, again, dependent on the material. But because the support pin is green, what this means is that the CAM software will leave that support pin during the finishing stage, and then at the very final last step, we're going to come in and actually finish that support pin away. So then you don't have to process or remove that, and we've accomplished what we needed, was the extra support throughout the milling process, and then the ease of cutting it out of the disc after the fact. So again, there's multiple ways you can skin the cat, but here is the semi-cuttable support pins, also another option. So if you're putting it in a place where you don't necessarily care if you have to come in and hand grind it down a little bit, but you still want to save some time cutting that off the machine, rather than the non-cuttable support pins, which are blue, we can make this red, which is a semi-cuttable, and you can see what it's going to do is a partial reduction on that support pin. So that way it's already kind of started, and if you've got like a disc or something like that, you can come in and lob those off really quickly. In some cases, you can even just push them out, pop them out by hand. Be careful about that with RPDs, obviously, because you've got very sensitive pieces where you connect your supports, particularly around these clasps. And what you'll notice is that I tend to place my supports as close as I can to the clasp. Now, this one right here has a little bit more heft. I'm not worried about, but the thinner the clasp gets, the closer you're going to want to get to the edge of that clasp with your support. And that's going to, again, prevent a cantilevered surface that can flex during the milling process. So those are some of the most important key factors to keep in mind when you're milling your RPDs. And then the very last step that I'm going to have here is when I go to do my calculation. So I'm going to save my toolpath at this stage, and I'm not going to actually calculate this, but I did want to show you these options here. So when we're going to mill it, Millbox gives you options for each job, and it really depends on what type of features your part has, depends on what choices you make. Now, on this particular case, I know that I have a lot of external undercuts, and because I want those to be milled out, particularly, especially in these pocketed teeth areas, I'm going to need to make sure that this option is selected to mill external undercuts. Now, I could either do this with 3+2, which essentially is index milling, and all that means is that the A and the B axis, the tilting and the rotation inside the machine, those are going to still occur, but it's going to index it at one position, and then you really only have 3 axes moving. So that's why we call it 3+2, because we still use the 2 rotation axes, but it's indexed, and then we're coming in with the tool and machining it. And what we'll do is we'll actually machine it, all those undercuts, from 4 different angles on each side of the disc. So it's like 8 operations total for the 3+2 operation. Versus 5-axis simultaneous, it allows us to really kind of rotate and tilt as the X, Y, and Z axes in the machine are milling. So that's why we call it simultaneous, because all axes are moving at the same time. And it accomplishes the same thing, but it does it in less time. So it's able to mill all the undercuts from the top side in one toolpath, all the undercuts from the bottom side in one toolpath. The differences are mainly going to be in the surface quality finish. The 3+2 gets you a little bit more overlap of surface finishing. So in some cases, you may have a little bit extra detail, versus the 5-axis, it's going to be, slightly less detail. And then in terms of calculation time, 3+2 being less complex of a toolpath is going to take less time to calculate, but because there's more of those tool paths, it's going to take more time to run on the machine. Versus 5-axis, because it's really complex, takes a lot of math. It takes a little bit more time to calculate, but significantly less time to run on the machine because of the reduced number of operations. So that's the other thing that you want to take into account with these particular parts. And so moving on from the RPD, because after this stage, we do our calculation and then we're left with a CNC file that we can then send to the machine, which in the case of a Roland would be a PRN file, but we can find those files very easily just by kind of pulling those up here. Let me move on to the teeth, because I think that's really important how those are imported. Let me go ahead and pull this up real quick, and we'll just import the denture tooth by itself and see how that comes in. So I'm going to choose PMMA for this. Now you could use a shaded PMMA, whatever you need, whatever material is available to you, and this would work out just fine. So I'm looking for denture tooth. All right, and notice this one was on its side in the preview process. So when I actually import this into the machine, and having your fixture visible this is a good reason that you want to have your fixture visible, because sometimes you might not necessarily notice that that's on its side. Now the undercuts are kind of a dead giveaway. Those kind of indicate to us, hey, there's undercuts here. Why are there undercuts on the occlusion? Well, that's because the part's laying on its side. So we want to fix that before this is actually imported. And ideally, again, you want to fix this in the CAD software, so that way you're not having to come in and correct this in the CAM. But if you do not have that capability, or you're not sure how to do that, correct it on the CAD, we can simply open up each of those files. And I'm going to click on Mesh Viewer right here, which opens up that free Lab 3D Explorer utility. And here it goes popping up. And this is just like a file explorer. So I can kind of browse through and see my files. Really nice thing here is, as I'm browsing through the files, I don't, how I had to click here to see the height. Lab 3D Explorer actually automatically displays the height of each of those parts, including, if it's going to be scaled in zirconia, or if it's going to be optimized. So again, really cool tools that are available to you, and this is free. So if I want to change the orientation of my part and I know it's incorrect, I can come through here, and you can try experimenting Y+, Y-, because maybe you're not sure which axis you need to rotate it along. Again, you can kind of go back. So if I do +90 and it doesn't work, I can just come back and do -90. In this case, it's along the X-axis that this particular part is out of sync. So all I'm doing is just clicking on the part, rotating along the X-axis. Now, if it's upside down, and you need to flip it 180 degrees, that's what this 180-degree flip or rotation is for. So just again, some tools that can help simplify that process. So now you can see the teeth have the correct occlusal orientation, and I can pull those in and then commence to nesting those particular parts. So it's going to take just a second here to import those, but actually let me move over to the other file where I've got those pulled in. So the only other thing that I mentioned on the denture teeth that you're going to want to look at, or these teeth for the RPD in particular, is you're really looking to stay out of these areas where you have these vertical walls or drop-offs. And you can really notice it if you look at it from a side angle. In some cases, it's going to be avoidable. But again, you can see my placement of my support pins on these particular cases. I tried to stick as close as possible to that equator line. And again, trying to stay away from the bottom of the denture teeth, because I know that that's where it's going to interface most. So honestly, you might even overshadow your support and have it mostly up on the occlusal side. So that way, again, you're doing less adjustments by the time you get over to the machine and you've cut parts off of the machine. Now, in terms of the milling times for the RPD, I think it was estimated around 43 minutes. And for these denture teeth, it should on average take about 10 to 15 minutes per tooth to be able to mill these out. So try to factor that in. We're close to, all in all, we're under an hour and a half, hour 45 minutes is kind of what we were looking at initially. So those are some of the main important aspects to consider. On the flip side, and again, Greg will touch on this probably when he talks to you guys about the tooling side. We mentioned that you save a ton of time. By utilizing smaller discs. Well, we can also save a ton of time by utilizing larger tooling. And that larger tooling allows us to physically remove more material, particularly in the roughing stage, before the finishing has to occur. Finishing usually is always going to be a set time. You can still reduce time by speeding up the feeds and speeds or by changing the step downs a little bit, but you're going to save the most time in the roughing because that's the bulk of the operation. We're cutting away the most material at that particular stage and process. So in this particular example, I'm just using a 2mm to kind of show you the roughing process, but you can see it's slow in general because we have to go layer by layer and we can only go at a certain increment with each pass. And so Sierra has worked hand in hand with us and with Zahn to be able to provide a kind of like a game-changing tool for desktop mills, which is the 3mm torque tool, and that's going to significantly reduce the amount of roughing time. Now, I don't know if I'd advocate using that tool on smaller discs, like in this case is a 10mm disc, but especially the larger your discs are, the deeper they are, 25, 30mm discs. Those are going to be good opportunities to use that larger tool that can then come through and really hog that material out. And so just one last thing to close on. I didn't necessarily plan on showing this, but it was a good kind of point that Carl brought up on the milling of the denture side. He mentioned you can have the negative and the positive of the patient ID and things like that. On the milling side, that doesn't necessarily turn out so well because, for example, if we were to place that on the side of this RPD, there's no access for the tool to come in from this direction to be able to mill that in great detail. So alternatively, what you can use is the engraving capability built into Millbox, and you can come in here and add some additional information. So if you wanted to come in and add the patient name and let's say today's date on there, I can do that, and holding the shift key and using the scroll key on my keyboard and then or on my mouse, sorry, and then using the control key and the scroll on my mouse, I can also come in here and add a unique ID. And what this is going to do, because the machine can see from the 180 side, we can use maybe a 0.3mm tool to come in and actually etch out this ID. So you can still kind of achieve the identification, but in this case, I think this would probably work out better on the milled side versus what comes out predetermined from the CAD. That usually is more conducive for printing, or it turns out better, I'd say, when you're printing the parts. So, all right, I think that just about covers what I had. One thing I do want to make mention is also, and I'm sure Greg might touch on this too. Sorry, Greg, I hope I'm not taking too much of your content, but there's also flat tools to consider, and this is more generalized for Roland customers and Millbox customers. With the newer updates, these tools are utilized for flat surfaces and will save you a lot of machining time in those examples. And also, in some cases, if you don't have those flat tools, you may not be able to get a properly seating restoration, because if there's a flat geometry and we're hitting it with a ball nose tool, of course we're going to leave behind a corner radius that could then impinge with your fitting. So just a very important thing to keep in mind there. And with that, we'll pass it on to Chris. So thank you guys for your time.
Yep, great, thanks, Mike. Yeah, I've used several different CAM softwares, and I will say that if anybody looked at what you did and felt in any way intimidated, it really does walk you through it. It really does just kind of step by step by step, and the next thing you know, you have a case nested and supported and it's ready to go. So yeah, I don't think anyone has to worry about the intimidation of dealing with softwares, because they definitely make them user friendly, that's for sure.
Yeah.
Great. Yeah, so now Ian, we got you all ready to roll. Let's take that case and let's see how your mill, those tools create a freaking rooster tail in there, ripping that plastic apart.
All right, thank you, Chris. Just to confirm, you guys can't see my screen. It's telling me you can. Just want to make sure you're seeing. All right, perfect. All right, everybody. Thank you for having us. Thank you for joining. My name is Ian O'Neill. I'm the Eastern U.S. sales rep with Roland DGShape. And I'm going to be talking to you today about our milling solutions, our DWX mills, and how they can be used or implemented for removable restorations. So I'm going to be talking a little bit about the equipment itself, what it can do, its functionality, and a lot about how this workflow can be utilized in different lab settings, depending on what type of lab you are. So let's go ahead and jump into this. I'll try to be as efficient as possible with my time. Just wait for this to.
I had to use the arrows on my keyboard.
Did you? All right.
Yeah, the click didn't work.
Perfect. All right, that helps. That's easier actually. All right, so why DGShape? So DGShape or Roland has a detailed history in prototyping. So through our history in other markets, it has brought us to where we are today in dental milling. So all of that history has brought us to the DWX52 DCI, which is our flagship machine. It is our 5-axis mill with a 6-puck changer inside of it, and has really made us the #1 choice for dental labs here in the US due to a number of factors: reliability, affordability, and its efficiency itself. So thank you to the US market for that. So our current product lineup, one of the mills that I'm really not going to be speaking about today because it doesn't apply in this scenario, would be our DWX42W, which is our 4-axis wet mill capable of milling block materials. And I'm going to be focusing more on the DWX52D and the DWX52 DCI. So I wouldn't be surprised if some of you on this webinar today have these machines in-house. I know Chris has the DCI in his location, and he used it here on this case. We did have the DWX50, the 51D, and now we have the predecessors to those mills, the 52 and the 52 DCI. So I'm going to talk really quickly about the DWX52D. The 52D, as I mentioned, is a 5-axis dry mill. This machine will come with 6 of those material adapters included with it, which is going to make the functionality of your used stocks much more seamless. The Millbox is going to keep track of your used inventory, and you're going to be able to keep those discs inside of those holders to swap them very quickly in and out of the machines themselves. So those adapters could be used on, Duracetyl, Acetyl, Duraflex, Zirconias, PMMA, wax materials, or even new materials like Trilor. So those would all fit as long as they're 98.5 millimeter disc. The machine itself does have automatic calibration functions. So it has a calibration device which is placed inside of the machine. There's no need to cut out blocks and measure them with a micrometer and enter the values, which ultimately is going to eliminate user error, a micrometer not being zeroed, and causing some complications inside your machine. So the thought process is keep everything simple and as efficient as possible. You're going to get the adapter rack to hold all of those material adapters. The machine runs off of the V panel, which is essentially the control panel for the machine, or the brain that tells it when to start, stop, calibrate, what your tool life is, and any maintenance procedures that you have to do. So that's downloadable from our website, and that is included with the mill. 5-axis simultaneous, so that 5-axis simultaneous kind of has your puck, as Mike mentioned. The puck and the machine kind of do the hula as it mills out your restoration itself. So that's kind of fun to watch. And the machine is controlled by precision ball screw drive system. So if any of you are familiar with the DWX50, that machine was a wire drive system. It was efficient and it worked very well, but over time those wires would stretch and it would cause for need for adjustments. So by moving to a ball screw drive system, there's less adjustments that need to be made, and those axes are going to actually move more slowly and more accurately, ultimately giving you a better restoration overall. The machine has automatic air control, so there's no longer need for you to adjust air pressure being blown into the machine depending on the material type that you're milling. And there's also an ionizer inside of the machine itself, which is going to reduce that static being inside of the machine from that compressed air. And if we have static inside the machine with a material milled like PMMA or plastics, it's going to stick to the inside of the machine. So that ionizer is going to help that debris drop to the bottom of the machine and be evacuated out of the back itself. A clean machine is a running machine, all right? So keep your machines tidy and they'll keep running for you. We have a user replaceable spindle in our dry mills. So anytime that spindle life does expire, you do have the ability as an end user to get the spindle, open that trap door in the back of the machine, and just the removal of a few screws, you can replace your own spindle, which is going to reduce your downtime if you do have an issue. Get that spindle overnighted to you. We have a video that's very detailed on our YouTube page, and it takes you step by step, turn by turn of those screws on how to replace that spindle yourself. So very nice option. You're not waiting for a technician to come out on site. We do have an optional cleaning tool, which will go inside the cavity of restorations at the end of the job and remove any mill debris from the cavities. And this machine has a 15 tool changer. So you can house up to 15 tools inside of this machine, which is great when you have, teams like the CIMSystems team and the Sierra team generating new tools and new strategies. Flat tools come out, the 3mm Horrocks. So it helps to have those extra options as well as having backup tools. So when you're running long jobs, maybe it's going to be overnight, you want to make sure that you have a backup tool in case that tool life expires. The machine and the software together would tell the machine when it finishes that operation and then has to go back to that tooling size, it's going to pick up the proper tool to continue the job. So it's a nice feature to have, especially while nobody's on site watching the mill. And last but not least, of course, is that nifty storage drawer on the bottom. We've all been in labs and we know how things can go missing. So it's nice to have that storage drawer, keep everything nice and organized. So we talked about the DWX52D. Now we'll talk about its big brother. These machines are virtually identical outside of the changer itself. They operate the same way. They have the same amount of axes and all of the same specs and features outside of the disc changer itself. So here we can see in this image, we have the 6 discs on the side and inside of that cabinet. And the traverser, the T-axis, will use a barcode system in connection with the PRN file that's generated, find the proper disc by using the barcode scanner, pick up that disc and transfer it over into the milling chamber itself. So that allows you to load up to 6 discs before you leave for the night. Maybe you're producing zirconia all day. At night, you're milling your plastic jobs. You load those in, start the mill, and go home for the night. And you come in the morning to completed restorations. So again, everything exactly the same there. So some quick specs about the machine itself. As I mentioned, the materials capable inside of this machine are zirconia wax, PMMA, composite resins, material like peak, pecton, or trilor, gypsum, fiberglass reinforced resin, and sinterable metals, as well as materials like Duraflex and Visiclear. So we have the spindle speed of 30,000 RPMs. We have 30 degrees of rotary in the B. We have very, very low air consumption inside of these machines, so it's not going to take down your compressor. You're not going to have to get a big dedicated compressor to be able to run the unit itself. The only thing that we use air for inside of these units is to blow away mill debris, which is important for keeping that mill debris away from the tool, which is going to extend life, bring down the possibility of, as Chris mentioned, that material softening and coming gummed up on the tool. So keeping that material moving away is best for milling PMMA and these acetyl materials. So it's obviously a bigger machine than the 52D, and uses 98.5 millimeter discs. The smallest thickness of puck would be a 10 millimeter puck that could be used inside of this machine. And for the DCI, the thickest puck that could be used inside of this device would be 35 millimeters of thickness. Now that is because the clamping system itself would only be able to hold that much space, and it has to do with that mail slot between the milling chamber and the changer itself. There's only a certain amount of space for that puck and material adapter to pass through itself. So maximum height of 35 millimeters. Okay. So the key benefits, I already touched on this a little bit, but 24-hour milling. Again, you can mill your zirconia all day if you already have one of these machines, and you're considering starting to dabble your removable department in digital removable. So 24-hour milling, allows you to run that machine with no one on site, load it up, go home, whether it's RPDs, mill denture bases with our TRK denture kit where you're pouring your own pucks. So it adds bandwidth to your laboratory, okay? Improved material management. So as we can see in the top image here, there's a whole variety of discs held inside of those adapters. So each CIMSystem Millbox software tied into our machines is going to be able to keep track of 26 discs at a time. So that's A through Z. So again, once you put that disc inside of that adapter, the thought process is to leave it in there until that disc is completely expired. All right. So maximizes your material management itself. So I mentioned the TRK kits that we have. So it gives you some unique options. Maybe if you don't have a printer, but you do have a mill and you're looking at digital denture, you can have the ability to pour your own pucks out of traditional denture acrylic and go ahead and mill them inside of one of our dry devices. So that's another presentation for another time. And last but not least is open architecture. So we want to keep the systems open. We don't want to keep the end user closed and confined into a box and locked into a system. As you want to try new materials or different options, we want you to have the ability to do so. So here at DGShape, that's not how we're looking to do business. We want to give you all the options possible. So again, I talked about those adapters. So if you're somebody who already has a 52D, maybe you're considering the addition of that 52 DCI. If you do add a DCI to your workflow, that Millbox software is going to keep track of the material adapters between those two machines. And those material adapters would be able to be transferred between the 52 or the 52 DCI. So you get 6 with each machine. You can buy them in additional 6 packs as well if you want to expand upon your library of used stocks. So the machines come with a 2-year warranty, which is going to cover everything except for consumables. Consumables would be considered something like a collet or a tool. This would also be repair. So it's going to cover everything for 2 years. Extended warranties are available at a very, very affordable price. So all of that said, the DCI itself gives you the ability to really diversify your production itself. Whether you're somebody who's only doing zirconia or you're a removable lab looking to buy your first mill or your first scanner, it gives you the ability to produce some different options. Zirconia during the day, so you can sinter overnight, plastic jobs at night because they're typically a longer milling process. Okay? Again, we kind of hit this point already quite a few times, but efficiency. How can you stay efficient? Mike put it best, if you're milling a restoration that's 16 millimeters of height, don't use a 25 or a 30 millimeter puck. You're wasting your time with calculations and milling time overall. But then when we talk about time, you also have to consider if you're milling unnecessary material, that's tool life, that's spindle life, that's suction unit life. These are all things that continue to add up. So making sure that you have stock of various pucks, regardless of what the thickness might be. Yeah, sure. Is it easier to just say, let's order only 30 millimeter pucks? Of course, but it's costing you more, and not just material cost, all of the things that I mentioned: tool life, spindle life, suction life, all of that, and your time. Okay. So maintenance, how does this change your maintenance processes for milling just zirconia? There really is no change in maintenance processes. We just would want to make sure, as I said, a clean machine is a running machine. Make sure your machine is clean. These are larger particles, larger shavings that are being generated than if you were just milling zirconia. Zirconia mill debris is a light powder. Think of holding flour in your hand and blowing on it. It's going to go everywhere. So that's going to be easier for the suction unit to evacuate out of the back itself. We're going to have the larger, heavier chips of plastic and PMMA. Though most of them are going to drop to the back, we are going to see in the corners of the machine a little bit of buildup. So after a few PMMA jobs or plastic Duraflex acetal restorations being milled, you should probably grab that 99-cent paintbrush from Ace Hardware and go ahead and turn the suction unit on and clear out all that debris. So yeah, maintenance. And the only other thing I would suggest is from time to time, maybe a couple of times a week, just make sure that the collet's tight. You don't have to remove it entirely. You're not going to wrench on that collet. You're going to make sure it's snug. Because there's so much torque on these harder materials, we want to make sure it's tight so we don't get any tool slippage, which could potentially give you a broken tool and a damaged restoration. So other than that, no real maintenance required. As far as calibration goes, calibrate as you see fit. When you set up the machine, make sure your machine is calibrated. If you move it to a new location, somebody comes in to clean underneath it and they move it, make sure you calibrate. But other than that, once you're calibrated and you're producing the restorations that you're expecting to produce and there's no unusual or irregular results, continue running until you're told to do so by our technical support team or your dealer. Okay. So which type of lab are you and how does this fit into your workflow? Maybe you're a fixed restorative laboratory and you're only producing crown and bridge work. Pretty common for those labs to be around. So having a DCI would give you the ability to recognize new revenue streams, right? Now you're able to produce different types of material that change your capability. Again, zirconia during the day so it can sinter overnight, plastic jobs in the evening when nobody's on site. It gives you the ability, maybe there's some local laboratories that you're friendly with, or maybe not so much, who knows? It gives you the ability to really become an outsourcing option for them. So it might be a removable lab down the street and you're the fixed lab down the street. They might not have a mill, they might not have a scanner, but maybe I'm sure they've heard about, Meyerson products and Duraflex, Acetal, VisiClear. Maybe they're interested, but they're just not willing to make the investment. This gives you the ability to extend maybe an olive branch in some cases and say, hey, let's work together. You'll get the ability to give this offering to your doctors, and we're going to use this as an outsourcing center. So great option there. And I believe Carl touched on it earlier. Designing is made easy with today's CAD systems. So the ability to scan texture and color, you can have a designer who's very experienced in all-on-4 restorations for zirconia, substructures, whatever it might be, and you have your removable technician or removable technician down the street. They take their model, they trace exactly what they want. Now that technician can take the scan and quickly design an RPD without needing to be a removable technician themselves, okay? So lots of options if you're a fixed restorative laboratory. Now, if you're full service, it's going to increase your productivity to have one of these DCI units in your lab. Again, producing all day, the idea is to start this machine and run it 24 hours. Never stop this machine from running. So additional bandwidth means more revenue, more product offerings for new materials. Okay. It also gives you the ability, if you're a full service lab and only milling zirconia, to take some of those traditional processes and cut out all those manual steps that Chris was talking about. So you don't have to go full digital with your removable. Start to work in some cases. Work out the kinks with your doctors. Figure out what works and what doesn't, and move forward. So give your business the ability to grow. If you're a removable laboratory, it allows you to stay cutting edge with your materials, right? So if you're producing your frames in metal and have been forever, now it gives you the ability to produce something in VisiClear, whether it's a tooth-borne clasp or a tissue-borne clasp. It gives you the flexibility to go to your accounts and say, hey, we're growing, we're offering new solutions. It's going to reduce the labor-intensive steps that most of your removable technicians are used to, and it also makes your lab zirconia capable. So if you become proficient with a 3Shape design system to design these RPDs, you can find a fixed restorative technician and have them come into your lab and be able to produce zirconia restorations, a brand new revenue stream. Or, as I mentioned before, even become an outsourcing option for somebody local who's not looking to make the investment to go digital. Okay, so that's really all I have for you right now, guys. And with that, Chris, I'll pass it back to you. And Greg, that's a beautiful machine you have sitting behind you.
Well, great. Yeah, it's funny. One of the coolest things about the machine is that keeping all your stuff collect. There's probably a second thought when they were designing that thing, but I love that little board underneath. But yeah, that machine, like I was saying, it has a rooster tail of material. At 3mm tools cutting through it, you can literally see this. It's like whenever you see a big speedboat and it has that big rooster tail of water, it's chewing through that stuff. So it definitely does a great job of doing that. And so here we'll let Greg talk about that big 3mm tool and talk to you about how that came about, and take it away, Greg.
Hey, thanks, Chris. And I'll start by saying I'm happy to be like the end cap on this presentation because for those of you who have stuck through the whole thing, the biggest trend that I would point out, or the biggest theme in this entire webinar, is the fact that our friends at Zahn have worked with all of us individual vendors to create a solution that works well for the lab. Individually, the vendor can do, we're all interested in delivering the biggest, best value to you as a lab technician or owner as we can, but individually, we cannot possibly do what we can do together with the Zahn team's help. So I think on behalf of everybody, I thank you guys for letting us do this presentation and demonstrating the value that this particular solution has for labs that are forward looking. And then secondly, before I get into my quick tool spiel, removables, if you look around, you ask anybody, you go around on the internet, social, this is the biggest growing part of our industry. And it's being driven by the demographic change in our population. Removables are really the future, and learning and being on the cutting edge and being able to process them digitally, in my opinion, is extremely important. And there are multiple ways to skin a cat, to use a phrase that Mike Webb used. But you know, what I think we've put together here is a really good process for repeatability, material options, and offering a value to your doctor. So we've ordered this presentation kind of in the same order as your workflow would be. You go through material design, nest, and machine. Now, often overlooked is the very, very end of that workflow. All of that energy is focused onto the tool, and if we skimp on that process, then all the precision in the world from the machine and the ball screws and the accuracy of the design, the ease of the cam, all that might not matter if you don't have the right tool in your place. So we're over at Sierra. We're always focused on helping tie all of that together and make it as efficient as possible through working with milling strategies and making sure everything works for you as an end user. I've got multiple slides here. This really isn't, like Chris outlined at the beginning, this is not a sales pitch. This is a couple of things that we see and experience with working with customers that might be of value if you're working in this sort of a new workflow. So we've got a couple of slides on how to work with tools. First off, you got to use a good tool. Sierra makes a good tool. Our bread and butter. We're only a dental company. We really know how to work with these materials in these machines, unlike any of our other competition, even worldwide. And so when you're using a Sierra product with a Roland product, with a CIMSystems product, Meyerson product, all together, you know that we've all done all the work on the back end to make sure you're going to get a result. And in my experience, I talked to a lot of labs. I've been in and out of this, quite a bit. And usually laboratories don't want to be R&D departments. Some of them are nerdy, like me, but most of the time you want to get a process. It's already been tried out. It's validated, and we can just punch out parts and make money. I hope I speak for anyone watching this when I say that. So a good tool is geometrically precise. All of our stuff is designed and manufactured to aerospace grade tolerances. So you could make a part of a Falcon 9 with our tool and make sure you're holding the spec. Okay, so that's really important when you want the same kind of quality to be coming off the machine over and over and over again. And the second biggest thing that we're looking at in kind of the innovation space is minimizing process time. Because the more stuff you can pump through that machine, the more money you can make with it, and the better ROI you're going to have on the system. And so Mike and I think Ian might have mentioned it too. But Sierra has developed a tool solution that's specific for removables. That's that 3mm toric tool, which is actually pictured here all the way to the right in my slide. That's a very efficient tool for removing material fast. And overall, on the front of machining plastics, we're reducing process times in the neighborhood of 30 to 40%, which means you can get a lot more parts off the machine. So I'm just going to run through my quick tips and tricks. This is my main spiel slide, and I'll just quickly run through the other 700 slides that I have queued. Okay, slide number 1. Cleanliness, guys. You got to keep everything clean. The mills like a daily suction, like make it part of your process. I like to use the word surgically clean. Build up on the shank, build up on the tool, build up in the machine. It just serves to be a cause of issues. So if you guys aren't vacuuming the machines out daily and giving them a nice little once over, I highly encourage you to start doing that. That's a 10-second slide. When we're setting the tools up, so if you go through your user manual for your Roland machine, there's a section in there that's going to talk to you how to load the tool in there. And by the way, I might be unique in saying this, but I keep my Roland user manual on my bedside table. It's wonderful nighttime reading. Memorize that thing, because the more you know out of that user manual, the more efficient and profitable you can do with the equipment. Memorize it. So when it comes to setting up a tool, and this actually applies to all tools, you have to put a ring on it. For the Roland system. Many people tend to put the tool through the ring business end first. You can damage the cutting edge of the business end of the tool by doing that. So we always say put the shank, which is the butt end of the tool, through first, position it into the little setting jig, and tighten everything down like the manual says. Secondly, when you make the installation into the actual tool holder in the machine, be careful you're not slamming the tool into the machine. Just do it gingerly and carefully. You'll cut down on user issues there. Okay, this is one of the biggest ones that I have conversations about. Collets. Ian glossed over collets real quick. When it comes to a machining process, you have your spindle, and I have props. I love props. This thing is holding the tool, and it's very important the tool is on center of the spindle. Any deviation from that center line is wobble. It's called runout. The biggest thing that affects runout is the condition and cleanliness of your collet, because it literally is centering the tool in the spindle. Constantly, like I like to see it done on a weekly basis. If you're in a production lab, pull the collet, make sure it's clean, the spindle's clean, put it back up properly torqued, clean it with isopropyl alcohol, make sure it's not damaged. And when you do see wear, replace it. You gotta replace it when you start seeing issues. And that again will cut down on a lot of your common milling support issues, like surface finish issues, chipped margins when you're doing zirconia, and all the things that cause people to call support. Focus on the collet. Okay, how many do I have? 695. All right. So I'm going to reiterate something that Mike Webb jumped on pretty quickly, is the milling strategy. That is literally the secret sauce to all of this. The way that we're driving the tool matters for the type of material, the type of part, and the machine, and the characteristics of the individual machine. All of that's decided by the design of the strategy. CIMSystems is one of the most forward-looking companies that really in this industry, and they're constantly iterating on this stuff. And I can't really say it enough. It's so important to use it. It's optional to upgrade the software, but it's every penny of it is worth it, because you're getting these innovations, you're getting these reductions in time, these increases in surface finish quality, reductions in steps for the workflow. Everybody wants you to be more efficient. So use the latest stuff, use the best strategies. It's all one big system. It's open, but we work together. All right. So, wow, I have 30 seconds. This is what we ended up with, guys, at the end of our process. And thanks, Chris, for the image. This is the file that we went through this exercise and designed and milled and produced. And frankly, it's a beautiful restoration. And this is the type of thing that you can get day in, day out, repeatably, when you implement these systems. So with that, I know that we're monitoring for questions. I'm happy to stick around, but you know, if you guys want to reach out to your Zon rep or anybody else on this, I'm sure we all be happy to help out with particular issues or workflows or, you know, questions around anything really. So with that, I'll shift it back to I guess Chris, you'll give us the outro. Chris, it's all yours. Thank you.
Yeah, there wasn't really questions. I think the big thing whenever you got so much information coming at you is again, you know, rely on Zon. You know, they're the ones who put this together. They're the ones we all work with. And so if you do have a question, I'm sure they'll be able to get you in contact with one of us. We can really talk to you guys even directly. So if you developed any questions, definitely contact your rep, and they can get you to the people that they can get those answered for you. I want to thank everybody. Yeah, it went really good. We all kind of ran a teeny bit long, but it's so much information. It's so difficult, and it's like I'd like this to go for another hour. So, but that's okay, right? I think everybody's going to be happy with all the information, this full, satisfying amount of information to take you from start to finish in producing one of these. So. Yeah, I didn't know if anybody else had anything to add, but I think we can let these people get back to work and think about maybe getting themselves a mill or getting themselves some updates or doing some of these jobs with some of these materials that they saw today. All right, great. Well, we will sign off now. And again, if anybody has any questions, just give us a contact. Thanks a lot, guys.
Thanks, everybody.
Thank you, guys.
Have a great day.